So welcome to lecture number 19 in the online mode. So in this class we are taking behavioral modeling. The subtopic is conditional statements. We could cover the structured procedures, initial and always block, procedural assignments, blocking and non-blocking, timing controls, delay-based, event-based, and level sensitive. So all these are completed. Now the next is the conditional statement, if else, and nested blocks. So let me go there. So conditional statements. Here we proceed. Before I proceed with these conditional statements, you just recall the C programming constructs. In C programming, you had studied the same kind of statements, right? So there, you had the syntax in the same fashion. If is a type 1, if else is a type 2, if else. So that is your nested if else. That was type 3 kind of syntax you have been using in your C programming. The same thing we are using here. Only changes a syntax. A syntax is partly changed here, rest everything is same. So in C programming, what we were doing is we were writing if and we were writing condition and then flower bracket open. If it is multiple statements, we are writing the statements here, close, else, again open bracket, write the statements, close. We were doing like this, right? So here in place of open brace and close brace, we will write begin and end. This is the only difference. Okay, so in Verilog only this is the difference, and here you need to check the condition. You need to check the condition. So this is a comparison in comparison with C language. Now we'll start studying about Verilog constructs of conditional statements, if else statement. Conditional statements are used for making decisions. Like if this happens, what should be my process? If this happens, what should be my other process, other action to be taken? So that is what you need to do here. So if else statement does a decision making upon certain condition. This condition you need to mention, like upon what the respective actions should be taken. So these conditions are used to decide whether or not a statement should be executed. Keywords used are if and else. There are three kinds of conditional statement: if, expression, true statement. If, expression, true statement. If this is not, expression is not validated to be true, then else statement should also be mentioned. Here what happens, if it is true it will execute, or else it will come out of the loop. Here it is not so. If it is true it will execute. If it is false, there is another statement which I am supposed to write it where it should be executed. In type 3, we have multiple condition check, multiple level of condition check, I can say. If expression, this to be true, this should be executed. If not, we have to check one more condition, that particular statement should be executed. If not, I have one more condition. So like that, we'll be checking multiple cases, multiple conditions, multiple level of conditional check, we say. So in that cases, we use a nested. We also call this as nested. Okay, a block must be grouped typically by using keywords begin, end. So if you have a multiple statements, group it with begin and end, like in your C program, open flower bracket and close flower bracket. A single statement need not to be grouped. Same rule follows as we studied in the previous sessions. Okay. So we have certain examples here. I have taken each individual example for each of the types. So let us go with example number 1. So in type 1, if there is a condition check not of lock, not of lock, and lock has a lot of many difference. You see, lock is equal to 0 means it implies not of lock, not of lock equal to 0. So this, see, if here the true cases if lock is equal to 0. False cases if lock is equal to 1. If lock is equal to 1, then it is false case. If it is 0, then it is true itself. Here it is not so. Not of lock. If true, if L is equal to 1 means you just here substitute lock is equal to 1. Yeah, I'm writing L in place of lock, okay, in order to save the time. So if I have 1 here, so L is equal to 1. Think that now L is equal to 1. 1, it's a negation, logical operator. Negation of 1 is 0. So 0 equal to 0 means it is true. True if L is equal to 1, lock is equal to 1. False if L is equal to 0. So exactly opposite. These things are opposite. Fine. So now you just see here, if not of lock, here there is no logic mentioned, right? So rather than mentioning like uh, this is equal to 0, right? Rather than mentioning like this, not of log equal to 0, we can mention in this way, equal to 1, sorry, equal to 1. This is equivalent to writing if not of log. Both are same. These things are same. Similarly, if log equal to 1 is equivalent to writing if log. Remember this. So now, whether this is 1, that we need to check. If it is 0, then it is false. If it is 1, then it is true. 0 if it is false. Now I'm checking not of lock. Not of lock should be 1 means lock should be 0. If lock is 0, negation of 0 is 1. So it means if lock is 0, then negation of lock is 1, then only buffer will be assigned with data. That's the meaning. Okay, so buffer data gets assigned to this only if lock is equal to 0. If lock is equal to 0, what happens? 0 negation is 1. Means if this is true, buffer gets a new data. That's the meaning. I hope the things are clear. Now, if enable, it is as good as writing if enable is equal to 1. That's the meaning. If enable is equal to 1, then out 1 is assigned with ANDed operation of I in 1 and I in 2. Out 2 is assigned with OR operation of I in 1 and I in 2. So you have a multiple statements, hence you have begin and end here. I hope the things are clear. Now, if number is less than max, the condition is mentioned in this manner. If a given number is less than max, max is I can say threshold value or a condition check variable. So to which I'm checking number. If number is less than max, then what happens? This condition executes. Else it will display that q full, try again. This is if else statement. Type 2 it is. Okay, it's a type 2. It is type 1 2 examples. Type 2, this is the first example. If this is true, I can say if this is true, this will execute. If this is false, else part. This is false statement. False statement will execute. Got it? I think things are clear. Very easy. Because the same things you have learned in your C program, I feel that you will not face any problem in understanding it. Okay. Now, you have, one second. Yeah, here. So you have, if ALU control is equal to 0, then y is equal to x plus z. So this kind of the analysis you have already come across, that is ALU. This is a ALU design. This is ALU control, select line. If that ALU control is 0, then addition should be performed. X and Z being the inputs, Y being the output. If I'm having one more condition. If ALU control is 1, then subtraction should happen. I'm having one more condition. So I use nested if else. Else if ALU control is 2, then multiplication should happen. If all the above three conditions are not satisfied, then what should happen? That is last comment. Else, no if here. So display invalid ALU control signal. We have only three operations to be done in this ALU. So first, each operations are done based on the select line, that is ALU underscore control. If control is 0, then addition, control is 1, subtraction, control is 2, multiplication. If 0, 1, 2, both three controls are not given, then this display command should be executed, or else any of these three things commands will be executed, expressions will be evaluated. So this is a conditional statement type 3 example. Now we shall have some codes here. I think half of the code is 1 second. Yeah, yeah, we shall proceed. So here we have two codes here for MUX design, 4:1 MUX design. Why I'm taking 4:1 MUX is it is simple to understand. That's why we are taking. So module MUX underscore 4 underscore 1, output is Y, S is a select line, I is a input, but we have not mentioned which is input and which is output in the module declaration. So we shall mention once we write module MUX. So here output is Y. We have been also declaring it as reg because we are using it in always block. Always remember, conditional statements are executed only if you use it in the initial or always block, or else it cannot be used. Remember that. You have to compulsorily use initial or always block. Okay. So when you use the output within the always block, then compulsorily you need to declare that particular respective outputs as register variable also. Either you can write it separately, or else you can combine it by writing output followed by reg followed by the output that you are focusing on, followed by input. So input select line is of 2 bits. Let me write a vector declaration for this. 1 down to 0, yes. Then you have inputs 3 down to 0, I3, I2, I1, I0, S1, S0. These are the inputs. Always at star. Star means what? Star means cover all the input variables. Rather than writing, it's equivalent to writing always at what all are my inputs? I ORed with yes. Rather than writing in this fashion, we can write it in this fashion. Or operation event or control for all the inputs that has been declared. Rather than writing like this, if you just write star, the meaning of the star is event occurring on any of the input specified. Event occurring on any of the input specified should behave as a sensitive variable. Means should trigger the execution of the always. If S changes, then also it should execute. If I changes, then also it should execute. That's what is the meaning of star mark. Okay. Event on anything or else any event. That's the meaning. Any event. Star means. Okay. So begin. Because we have multiple statements, I'm using if statement here. If S of 0 is equal to 0 and S1 of 0 is equal to 0, ANDed operation. If both are 0, this as well as this both are 0, then y should be allotted with I naught. If s is 0, s naught is 0 and s1 is 1, I1 should be allotted with y. 1 0, I2 should be allotted. 1 1, y3 should be allotted. End module. This is with type 1. In type 2, up till here it is same. See, up till here it is same. Here also it is same. What is the change in the body of the module? Rather than after if statements, your first condition check we have done. If this does not happen, then we are checking one more condition, nested if it is. Okay. So nested if else is we are checking one more condition. Here it is. We are checking one more condition, it goes on. Here else part has not been put, here else if has been put. So this is a type 1 if statement alone. This is type 2 and 3 because we have used if else statement and its nested form also. So these are the two codes. Let me just take it in the Xilinx website, Xilinx platform and explain you the concept. I'll take the code from here itself. MUX underscore 4 underscore 1. Xilinx. So new project. Let me just take the project of unit 3 itself. One second. I'll take the unit 3 unit 3 example. Let me open one more. Unit 3 examples of conditional. Okay. So conditional statements. Let me open this project so that all related to if else statements. Here I was working on some project of my research. So I have used Vertex kit. Okay. So image reading, BRAM, all this concept I was trying. So there I was using other kit. Let me change that kit. So we had Spartan 6, LX LX4 TQG. Yes, now it's fine. Yes. So this is your project. Let me take the new Verilog model. Verilog Verilog module. So MUX underscore 4 underscore 1. So next, finish. I'm just copying the code in order to save the time. I'll zoom it. Hope it is visible. And module is done. MUX 4 is to 1 MUX. So this is a code, right? Same code. Let me save it and synthesize it. And you can have a test bench for writing it, or else you can just give some test cases and check manually, I can say. In ICM simulator, how you were doing before you understood stimulus block writing, you were doing manually, right? So you can do it in that fashion also. Let me do in that fashion. So I'm using only if statement. Very next to it, we just write else here. Okay, that's the only difference, right? We have only else written. Rest everything is same. So synthesis process is taking place. Almost it's done. So there is some warning. Let us check what is that warning. Sorry. Warning is 1 bit latch of the signal. Latches may be generated from incomplete cases of statement. We do not recommend latches. So it is telling that there is 1 bit. What is this warning? So of course this warning is not troubling you, but still why I'm taking this example, because why I'm just want you to understand it, because uh, one second. Just so here um, in MUX, what happens actually? You have you have you have a lot of in 4 is to 1 MUX out. This is AND gate output. All these things combinedly we connect it to Y actually. We connect it to Y. Now Y is 1 bit. This is 1 bit, but 4 bits are coming to it. 4 bits are coming to it. Of course, here we were putting OR resolution, OR gate. But in Xilinx simulator, it will not consider OR gate, because in order to optimize it. So when 4 bits are being forced to single bit, it has to make some selection, which bit it wants to give the importance, right? So in such cases, we are bound to get the warnings like this. Okay. So found 1 bit latch for the signal Y. Okay. So this code synthesized simulation. Highlight this ISM simulator, simulate behavioral model. It is taking some time. Yes, here it is. Let me restart it. I give the select line, force constant, as 0 0, and I force the input as force constant as it is I3 to I3 down to 0. So I force it as 0 0 0 1. Okay, I'll run it. You can see here y is 1 because it has selected I of naught. I'll maximize it. This is I of naught is 0, and S1 and S0 both are 0 0. Hence it will select y. So of course I'll show it with one more example. Force constant, I select now 1 1, which is 0. It has to be 0 just here. It is 0. Y is equal to 0 for selection of 1 1 as an input. Okay. So this is a simple 4 is to 1 mux. We have been thorough with this from long ago. So if you write else here, so it go on checking one condition one after the other. That's the only difference. No difference, much of the difference here. I think not needed to explain it again because it is very simple. We shall take some other example. So here, if else if statement, you'll get the same output. Okay. So I don't think it's much needed for explanation. So next one, comparator. I'll take this code into the Xilinx environment. It has popped up. Let me close it. So once again, I don't want to repeat the process because it is same analysis. So here, 2-bit comparator. So you have 2-bit comparator design given here. So if I want to show you the block diagram of this 2-bit comparator, you have A and B, which is of 2 bits and 2 bits, and you have 3 outputs, which is of single bits. Single bits. This is A greater than B, A L B means A less than B, A equal to B, right? So if A is greater than B, then this should be 1, rest all should be 0. If A is less than B, then this should be 1, rest all to be 0. If A and B both are equal, A equal to B should be activated. So module comparator A, B, AEB, AGB, ALB I have written. So outputs I have declared it as reg because I'm using it in the always block. Reg and always. Remember, these two are interlinked. So AGB, ALB, AEB, all these are single bits. Inputs are 2 bits. This is 2 bit. A1, A0, B1, B0. So begin. I'm using if else statement. See how easy it is. If A is equal to B, I'm checking this. If these two things are equal, if A and B are equal, then how should be the output? AEB should be 1, other two output should be 0. Else, I'm checking one more condition. A less than B. ALB should be 1 because A less than B. Both other output should be 0. Else, again, this condition is optional. If you leave it also, it doesn't matter. Okay, because this is the only condition left now. If you just ignore it also, it will check. Just write else, check it, or else you can write it, no problem. A greater than B is 1, rest everything is 0. So very simple, right? We shall take this code into the Xilinx simulator. So copy. So what's the name given to it? Comp underscore 2 underscore bit. Verilog module. Comp underscore 2 underscore bit. Comparator 2 bit. That's the meaning. So comp underscore 2 underscore bit. So let me zoom it. So same code it is. It's the same code. Save it. So it is not set as top module. Let it be to save some time. We'll just check syntax because it will definitely work. Quickly we'll move on to the simulation. Manual simulation. We use ICM simulators options. So I highlight comp underscore 2 underscore bit, simulate behavioral model. We shall check whether it is working fine, because we used to put lot of efforts in order to write its truth table, K-map, as well as K-map table expressions. Those expressions we are writing in the Verilog code. So that is a way we preferred in gate level modeling as well as data flow modeling. In behavioral modeling, it's a structured, it's an algorithmic program. If you just write the algorithm, it works fine. So parallel hardware will be generated by the Xilinx itself. So restart. So A force constant, let me just give it as 1 1. B force constant, let me give it as 1 0. Means A is greater now. Let me check if it is working. So you can check. A is greater than B. So EGB is working. Now, so I make both are equal. Force constant, I am making B also 1. So A equal to B should work now. You can see here. A equal to B is 1. Now we shall make A less than B. A will set to less number. Constant. A is 0 0 or 0 1. Let me check. So if I run it, you can see here A less than B is executed. Perfectly it is working. So this behavioral style of modeling greatly reduces our work of programming. So this is an advantage actually over gate level modeling and data flow modeling. We heavily use a behavioral style of modeling in Verilog coding. So very next is D flip-flop. So D flip-flop is the next example using if else statement. You have a D flip-flop here. So here module D underscore FF, clock reset D, all these are inputs, Q and QB are your outputs. Your inputs are clock reset D, outputs are QB. As always statements you are using in order to define the output. So we are using reg also. It's a reg, register variable. So initial begin. So why I'm using this initial block is to just for initialization purpose. So this block is just for initialization purpose. You can use this or you can even use other method also. Okay. So after that my main code starts always statement. Always at pause edge of the clock you see here. This is very important. This is an event timing control. It is whenever there is a pause edge of the clock. If it is clock, only in these areas it will be active, because here it is pause edge. Only these area it will be active. These area, whenever these area is encountered, then only always block will be executed. Begin, because multiple statements are there. If reset means it's as good as writing if reset is equal to 1. That's the meaning. If reset is equal to 1, q should be 0. And you know that qb is always inverted version of q. So no need to worry much about it. End means multiple statements. That's why end. Else again begin, multiple statements. That's why I'm having it. If reset is 0, then else part will be executed. That is q is equal to d. So qb is again the inverted version of q. So this end is for this begin. Okay, and this end is for this begin, not this one, this begin, because this begin has ended here, else begin has ended here, always begin has ended here. So that's it. This is end module. So let me take the same example. So copy d underscore ff. So that's our new Verilog module, d underscore ff, new source Verilog module d underscore ff. Next, finish. Okay, so here I'm copying the code. Half the code I have copied, rest half is here. So I'm copying that also. So here you have the full code, same code. I said that there are other ways. See, I'll show you one more way of writing it. So this output, what I do is This is equivalent of writing this. Okay, you can see here output reg initialization. I did it here itself. That is also accepted. Even this way is also accepted. This way also accepted. Your wish you feel, whatever way you feel comfortable, you can prefer that. So it's D flip flop. Check syntax. Any code can be written in 100 ways. So whatever code you like, you can prefer that way of writing. Only thing is you should follow the rules and discipline of that particular programming language. So that's why if you ask me to write the D flip flop code tomorrow, I may end up writing in different way itself. Okay, so that's how it goes. So D flip flop, simulate behavioral model. So D flip flop, it should be sensitive only at the edges of the clock. That we are just wanted to check. Let us check that. So here I'll just don't restart it now because initial values I have given. If you restart it, initial values will be lost. So don't restart it. So force clock, leading edge is 0, trailing edge is 1, 10 nanoseconds is your period of the clock. So this is a period of the clock, 10 nanoseconds. Okay, click on OK. So reset, constant. If reset is 1, you'll see what happens. After that, we'll change it to um, other thing. So D flip flop, D data input, I'll make it to force it to 1. That's it. So we'll run it. So we'll zoom to it. You can see here. You can see here. Whenever there is a pause edge, I would have set it as it is microsecond. So I would have set it as nanosecond to show it. Let me show it. Let me show it here. Okay. So here I'll change it to nanosecond. Here 10 nanoseconds. Every time I run for 10 nanoseconds. So now you just hear. I'll run it again, specified time. So 10 nanoseconds. So at positive edge, this is a positive edge. Reset is 1. So irrespective of it, your Q is maintained to be 0. Q is maintained to be 0. Now what I do is I change the reset to 0. Now you see here D is getting updated. So D is 1. So it'll be assigned to Q and QB will change its value. Run it. So you can see here this is a positive edge. At positive edge, what is happening? D is 1 and that has been assigned to Q, and Q inversion version is assigned to QB, and it continues like that. Okay, so now if I force D value to be 0, sorry, force constant D value, I'm forcing it to be 0. So you can see that this will toggle, means not toggle, this will change its logic 1 to 0. So see here 1 to 0 at this positive edge. At positive edge itself, it is changing its logic. So this was a D flip flop. Okay, very simple. So this you take it as a task for as a homework. You please implement D flip flop in your respective laptops in Xilinx environment. If you have any problem while writing the code for it, executing the code for it, let me know it. Okay. Next is T flip flop. So T flip flop goes like this. So you have T clock QQB inputs, T clock output reg QQB initial. Let it be this initial values. Always pause edge of clock begin. So here if T is equal to 1, toggling should be happen. QB should be toggled. Uh, you know, Toggling. How to represent toggling? Toggling is represented as C. If Q is equal to inverted of itself means if it will follow, think that is Q. Now it is 0. So after some time, so when Q is equal to not of Q, it will go like this. It will become after some time again when you encounter this statement, Q is 1, it will go to 1. So this will toggle. Okay, and QB is inverted version of Q. No need to change it. Retain it as it is in your D flip flop. So else begin Q is equal to Q if T is equal to 1. QB is equal to QB because toggling should not happen. So it should continue in the same state. So this code let us take in the Xilinx environment. So T underscore FF is your um, module name. Let me just go to implementation, new source, Verilog module, T underscore F. ff. Next, input and outputs are specified. I'll just copy paste it. So here's a code. Let me just copy it and paste it. So it's copied. I'll copy the rest of the code. Rest of the code is copied. So this is a code, same code. Let me just highlight that t underscore ff and check syntax it. Save and check syntax. So it's checking the syntax. In between, I'll zoom it for you. So here you can see here. In initial, you can even mention that QB is inverted version of Q, where Q is mentioned as 0. And that is also possible. Okay. If t is equal to 1, Q should be toggled. And even QB should be toggled in the other way, opposite way of Q. Else, it should maintain the same way or maintain the previous state. So T flip-flop simulate behavioral model. Simulate behavioral model. Let it generate. I have so many examples, counter examples. I think if else statement, so important that you can solve so many examples. Okay. So don't restart it because you've initialized it. So initially I force clock. So in force clock, leading edge is 0, trailing edge is 1. If you mention 1 nanosecond, think that you mentioned 1 nanosecond as a period. Okay. Here I want to run at specified time. I want to run for 1 nanosecond only. When you click that, the simulation runs for only 1 nanosecond. That's the meaning. Clock is done. T. So T I forced to be 1. Let me check the toggle case first. T is 1. So run for the specified time. Zoom to fit. Zoom out. Uh, yeah, here it is happening. Okay. So at positive edge T is equal to 1, Q is toggling. At positive edge T is still 1, so again it toggles. At positive edge T is equal to 1, again it is toggling. So it's continuously toggling. You just hear Q and QBs are continuously toggling. Now if I force T is equal to 0, T is equal to 0, then it will maintain the previous state. What is the present state now? Q is equal to 1, QB is equal to 0. Same state will be maintained throughout. See here, same state is maintaining throughout. This is a T flip-flop. Okay. So T flip-flop and D flip-flop, both these things have been explained. So using Xilinx simulator, in the similar way, you have SR flip-flop and JK flip-flop. So you have SR flip-flop here. So in the SR flip-flop, input are S and R and clock, outputs are Q and QB. Your always statement, so you should use it here because there are multiple checks, multiple variable checks, I can say. So what I have to do in this fashion? I have S and R to be checked. If S and R both are 0, then how to write it? Negation of S, negation of R. If both are 0, then Q should maintain its previous state. If S is 0 and R is 1, this is 0 and this is 1. This is how you need to write 0 and 1. Means, see, if S is 0, R is 0. Negation of 0 is 1. Negation of R is 1. So this will result in 1. This is result in 1. Totally it is 1. If 1 means if S is equal to 0, R is equal to 0, this will evaluate to be 1 because this is S bar and R bar. Here, when S is 0, this is 1. When R is 0, it is 1. When S is 0, it is 1. When R is 0, this is 1. This is 0. So when I say S equal to 0, it is S bar is equal to 1. So S bar is equal to 1, T bar, R bar is equal to 1. When it is ANDed, it is 1. If this is 1, this is going to execute, definitely. So when this is executed, Q is maintaining previous state. In this case, this is 1 and this is 0, it will evaluate to be 0. So this will not evaluate. So next it will come, it will not evaluate. So hence, this is executed. When this is executed, it will come out of the loop. Q bar is inverted version of Q. So when special case, when 1 1 undefined state, so here S bar R bar is 0 0. So else statement will execute. No three condition checks are possible, are valid here. So it will execute undefined state as don't care. Q also don't care. Q bar will also be don't care. Okay, because Q is undefined value. So this is the SR flip-flop. Similarly, JK flip-flop, JK are the inputs, rest everything is same. If J and K are 0, 0, maintain the same state. If 0, 1, follow the J value. If J is 0, Q is 0. If J is 1, Q is 1. Else, you should follow the toggle case. This is toggling case. So this I want you people to check, take it as a task for you. So check it and tell me whether you are getting the output for the SR flip-flop and JK flip-flop as expected in your Xilinx environment. Those who have already installed Xilinx in your laptops, please check it, test it. If you have any doubts, let us take it in the next class. Okay. So that's it for today. If you have any doubts, let us have the discussions.